Welcome to a new video of my series about GNU/Linux and USB. In today's video I will show you how to turn this Atmega32U4 microcontroller into a first simple Hello World USB device. So the goal for today's video is to write a program on this microcontroller so we can detect this USB device with lsusb, because currently you can just see my peripherals here. And normally I love live coding, but today it will be a little bit too much. And I have to admit I haven't written this code for this USB controller by myself. I got it from this webpage here. So Guiweiler wrote this library initially and I just took it. I translated all the comments from German to English and I deleted the parts I don't need to make it a little bit more easier to understand. So, and today we will go over this code. So most of it is very chip specific, but you will get also an overall view what you have to do to write your own USB device. Maybe later I will write a similar USB device on other microcontrollers, but for now we will start with the Atmega32U4. Okay, so let me show you what we got here. So here in this folder we have the following files. So a main.c file, which contains our main function, a makefile to build the code in the library folder, and in this library folder we have two files. Here we have the source code for the USB library and we have a header file for the USB library. And now let's look at all of them. Maybe let's start with the main.c file here. So the main.c file is quite simple. All I'm doing here is I'm including the USB library, and here in the main function I'm overwriting a fuse bit. I start the USB IP with this USB init device function, and then I initialize a GPIO for an LED and I toggle it every 500 milliseconds. And everything which is USB related will happen in interrupt service routines which are implemented in the USB library. So here, all we do in the main function is toggling this LED here. Okay, and now let's open up the header file of the library. And let's see what's in here. Okay, so here we have some macros. So here we have a macro for setting a bit in a register. For clearing and setting a bit. Up here we have clearing, so we are just clearing one bit of this register here. Here we are setting one bit of this register here. And here we have two macros to give us the lower 8-bit of a 16-bit value, and here we have a macro for giving us the higher 8-bit of a 16-bit integer and shifting it by 8. Okay. Down here we are defining a prescaler for our PLL. So there's a PLL integrated in this microcontroller for the USB IP, and the prescaler for a 60 MHz crystal which is used here on my board is 16. Okay, and now we are defining the endpoints. For every endpoint we have to set up the type of the endpoint. So we have the 4 types: control, isochron, bulk, and interrupt. Then we have the direction, which could be out or in, but not for a control endpoint, because there the direction doesn't matter because it supports both directions. Then we have the size of the endpoint in bytes. So, and one thing about this microcontroller is only endpoint 1 can be up to 256 bytes. All other endpoints just can be 64 bytes in size. But this is something related to this microcontroller and other microcontrollers. It doesn't have this limitation. The problem is the Atmega32U4 has just about 800 bytes SRAM for the endpoints buffers. Okay, and down here we can decide if we want to have 1 bank or 2 banks, and then we can define all this for the endpoints. But for a simple Hello World USB device, I just need to implement endpoint 0. So all I have here is endpoint 0. Endpoint 0 is from the type control. the direction don't care for a control endpoint. The size is 8 bytes, and I will use one bank. And down here I'm defining the size once again, which is 8 bits. Okay. And down here I can define the total number of endpoints without endpoint 0, and I don't have any additional endpoints, so I set this to 0. And this is the length of the configuration descriptor, and this depends on the number of endpoints which are implemented. So in our case it's just 18 bytes because this here will be 0. Okay, then we have some status codes defining some string descriptors. So here number 0 is the language descriptor, number 1 the manufacturer string, the product string, the serial number string. And down here we have the functions implemented by the library. So here we have the USB init device function, which we have already seen in the main file. Then we have here the USB init endpoint function, the USB endpoint 0 setup function, and the USB send descriptor function. And that's all. Okay, so let's jump to the source code. So I already told you everything will happen inside of interrupt service routines. So this interrupt is triggered when a reset was applied to the USB IP. And what we are doing here is we are checking what type of interrupt occurred. And here, this register is one of the interrupt registers of the USB IP, and we are checking if the end of reset interrupt is set, and if so, we are clearing this interrupt, and we init endpoint 0. Therefore, we are calling the function USB init endpoint. We want to init endpoint 0, and we are passing these arguments here, which we have defined in the header file before. And the next thing which we are doing is we are enable the other USB interrupts here. So here in the USB interrupts register, we are setting the RX interrupt to be enabled. And now every time we receive a package, we will call this interrupt service routine here. And in this register here, we can find the destination, so which endpoint the received package belongs to. In case if it's 1, it's a package for endpoint 0, so we are selecting endpoint 0 here to be the active endpoint. Down here we are checking if if we have received a setup package, and if so, we are calling the USB endpoint 0 setup function, which we will take a look later. And if you would have additional interrupts, for example, if the uint value is set to 2, we have a package for endpoint 1. If it's 4, we have a packet for endpoint 2, and so on and so forth. But here I have only implemented endpoint 0 because I don't need anything more for a simple hello world USB device. Okay, the next function we have is the USB init device. So first we have to enable the USB IP, which we're doing in these 2 lines of codes here. Then we are shutting the USB IP down. We are starting the PLL. Here we are applying the prescaler. Then we are waiting for the PLL to lock so that the PLL reaches its final frequency. And then we are activating the USB device once again, and we are enable the global interrupts. That's all this function does. Okay, here we have a function for activating a USB endpoint. We are giving the following arguments to it. First argument is the number of endpoint we want to enable. Then we have the type again, the direction, the size, and the bank. And you have to know, this microcontroller has about 800 bytes of RAM for USB packages. and we have to allocate some memory of this SRAM for every endpoint. The way we are doing is we are setting the desired endpoint number here. Then we are enabling the endpoint. Here we are setting the size, direction, type, and so on in these two lines here. And then we say, please allocate the desired memory for this endpoint. And by doing so, we have allocated the memory for this endpoint. So this is what we have done up here. So we just initialize endpoint 0 here. Okay, and now let's say we have received a setup packet for the endpoint 0 during USB enumeration. So what we are doing now is we're setting endpoint 0 the active endpoint. And if it's a setup package, we are calling this USB endpoint 0 setup function here. So let's take a look at it. Up here we are just defining some variables, because a setup package always contains the following fields. The first field is the request type. From the request type you can get the direction and the request type of the setup package. Then we have a request number. Then we have a 16-byte value field, and we have split it here to value low and value high. Then we have a 16-bit index field and a 16-bit length field, and then we have sometimes some additional data, and that's how a configuration request looks like. Okay, and down here we are writing the USB descriptors into the flash of the microcontroller. Because if you remember my previous video, we have seen this slide here. So we have a device descriptor, configuration descriptor, an interface descriptor, and an endpoint descriptor. And now we have to write all these descriptors into flash. And this is what is done here. So the first descriptor is the device descriptor. The device descriptor has descriptor type 1, and it contains some class codes here, then the size of endpoint 0, which is 8 bytes. Then we have a vendor and a product ID, and I borrowed here the vendor ID from Atmel, which was the producer of this chip, and for product ID I set to 1. And then we have the information about our string descriptors. So here we have our manufacturer index is 1, product index is 2, and serial number index is 3. We will see this later. And the next important thing is the number of available configurations. So if you remember the last video, a USB device can have multiple configurations. For example, a firmware flashing mode and a normal operation mode. But in this case, we just have one available configuration. Okay, and next we have the configuration descriptor. So the first byte here is again the length of the descriptor, which is 9 bytes. Then we have the descriptor type, which is 2. This indicates this is the configuration descriptor. And what are important values here? Yeah, maybe this one here. So here we are saying the maximum power consumption of the device is 500 milliampere. So here 1 unit counts for 2 milliampere. Okay, and the next important thing is the number of available interfaces. Here I say we have 1 available interface. Okay, then we have the interface descriptor. The length again is 9 bytes. The descriptor type is 4, so 4 stands for interface descriptor. Then the interface descriptor contains the number of endpoints, which is 0 in this case. And we have some interface class codes, which I have set to FF, which means custom interface class. And down here we have the index for the string descriptor of the interface, which is 0 here. And that's it. If we would have some endpoints, here there would be space for the endpoint descriptors here. Okay. And then we have some string descriptors. So the first one here is the language descriptor, and it's 4 bytes in size, and we're setting it to English USA. And you have to know all string descriptors are encoded as Unicode strings, so they're 16 bits in size. So here we have a manufacturer descriptor, which is 24 bytes long. The descriptor type is free, this means string descriptor, and I've set this to bright light, and you see because it's 16-bit Unicode string, I have to add this padding 0 after every ASCII char here. Okay, then here we have the product string descriptor, and I've used test device here. The serial number is 1, 2, 3, 4, and that's about it. Then we could have some endpoint descriptor, but we don't have any endpoints, so it's okay. Okay, good. So we have received our control transfer package. Now we have to read the package information out of the SRAM, and we can do this by accessing the USB data registers here. And it's a FIFO, so first in, first out stack. So we are reading them out one by one. And here we are, as the length is split into a low and a high value, we are calculating the total length here. Then we acknowledge the setup package by resetting the received setup package flag in the interrupt register. Yes, this will acknowledge the package. Okay, and I already told you the request type tells us which request type we have. And if bit 5 and 6 is set to 0, we have a standard request. Standard device requests are used during USB enumerations, so let's take a look at it. Good. And here in bRequest we can find the number of requests. So they are defined by the USB specification, and here we are listing some of them. So let's start with request 0. This is the get status request. It has 3 phases, so we have a setup package, a data phase, and an acknowledge phase. The direction here is in transfer, so we are transferring data from the PC, from the USB device to the PC. And now the microcontroller has to send back a 16-bit value for the status. And we can do this by just writing to the UE data X register, and I will write 2 times a 0 to it. So this means the device is not self-powered, there is no wake up, and it's not halted. Okay, then we are clearing the TXINI flag, and this signalizes to the USB to the PC we are now ready for a new IM package. Then we are waiting for the 0 length package from the host. This is the acknowledgement of the host. It received these 2 bytes here, and then we are clearing the flag that we have received the 0 length package. Okay, so if the request is 5, we have the set address command. This is just a 2-phase transaction with no data phase, and the direction here is out. So in the value low field, we have the address of we have our new USB address for our device. Because on startup the address is 0, and here the PC can set an address. So we are setting the address. We are acknowledging the package. Yeah, in this wrong here, this should be out package. And yeah, then we are waiting for the CLP to be sent. And then we're enabling the address by setting bit 7 of the USB address register here. And then we have our new active address. Okay, and now the next request is 6. And this is the phase where we are, or where the PC is requesting the descriptors of the USB device. And the desired descriptor can be found in the upper 8 bits of the value field. So in case of 1, we have to send the device descriptor. So here we are getting the size, which is the first bit of the device descriptor, and then we are calling this function to send the USB descriptor. In case of 2, we want to send the configuration descriptor. Once again, this works quite similar. Here we are checking the length, and then we are calling this USB send descriptor function to send it. Then here we have, if the request field is free, we want to, the PC wants to get the string descriptors, and in the lower 8 bits of the value field we can find the desired descriptor. Yeah, so here we can find out if it wants the language descriptor, the manufacturer descriptor, the product descriptor, or the serial number string descriptor, and we're all sending it over this USB send descriptor function, which we'll take a look in just a minute. And then we have this transfer. So if request is 9, we have a set configuration request. This is again an out request. If we would have endpoints, we would have to reset them, but as we don't have any endpoints except for endpoint 0, I will just send the serial length package, and I will wait for the serial length package to be sent, and that's it. And in case nothing of the above is true, so if we have request 10, for example, I will send a stall request to tell the PC, hey, I don't support this request. And in case if we don't have a standard request, I will also tell the device, hey, I don't support this, by sending a stall request, or stall response, sorry. Okay, so this was the USB endpoint 0 setup function. Now let's take a look at this send string descriptor function. So first argument here is the descriptor we want to send. Second one is the number of bytes of the descriptor. And here we are just going through every byte of the descriptor. It could be the PC aborts the transmission. So it says, okay, I don't need any more information, so stop the transmission. If so, this RX out, so received out transfer will be set, and then we will abort this function. If not, we will put the current data into our data register, and if 8 bytes, which is the size of the endpoint or of endpoint 0, are put into this data X register, we will send the data and wait for the acknowledge of the host. And in case this length is, the descriptor length is not modulo 8 is unequal to 0, we will send the remaining data here, and then we are acknowledging the last 0 length package from the host, and then the handshake is done. Okay, that's it, quite a lot. In case my explanation were too fast to you, I will put some useful links into the description so you can read over it, and then hopefully my video makes a little bit more sense. But this was a brief overview about what has to be done to get the USB interface of my Atmega32U4 microcontroller up and running. So now let's take a last look at the make file. So all I'm doing here, I'm specifying the CPU frequency and the type of CPU here, and I want lib to be my include folder. So here we have the sources I want to compile. The target should be USB hello. Here I'm compiling it. Here I'm converting it from ELF to an hex file. And here in the clean target, I'm just removing the build files. So let's build it. And now let's flash it with my USBasp programmer here. But before, let's count the number of available USB devices. So this is 40 now. And now I will flash the device. So the programmer is USBasp. The controller I'm using is Atmega32U4. And I want to write to the flash, and I want to write USB hello.hex to the flash. So let's do this. I will give it my password. Okay, it's writing. Okay, it's looking good. Now you can see the LED is blinking, so our program is up and running. And if I count the available USB devices, you can see there are now 15. If I execute lsusb, you can see we have a new device here from the Atmega Corporation. So this is our new device. So let's get some more information about this device, but let me check how. Okay, I think, yeah. And bus 37, yeah, here we can see some more information. So here we have our device descriptor. The length is 18 bytes. The maximum packet size is 8. We have the vendor ID from Atmel and the product ID 1. Here we have the manufacturer string, which is bright LED. We have the product string, which is test device, and we have the serial number 1234. We have one configuration. So the maximum power is 500 milliampere. And down here we have our interface with no endpoints. Okay, great. So our simple Hello World USB device works. I know this was a quite hard session and it was quite chip specific. If you would have another chip, it would look a little bit different. But I hope you've learned something and enjoyed the video. Next time I will write a Linux driver for this simple Hello World USB device. So if you want to support my work, you can buy my coffee on buymeacoffee.com/Jonas for Linux. So that's it for today. Thanks for watching and goodbye.